Hello, this is Mrs. Poland, and today I'd like to go over the concept of the power of a test. The power of test can be looked at in two different ways. The first is the power of the test is the probability of rejecting the null hypothesis when in fact the null hypothesis is false. The second way is the power of a test is the probability of not making a type 2 error. And we call that beta. So the power of the test is actually 1 minus beta. In other words, it's the complement of the probability of making a type 2 error. The following diagram can help you understand the relationship between making a type 1 error, a type 2 error, and the power of the test. The top normal curve that we see here is based on the null hypothesis. So we can see from the diagram that the mean looks like it's 0.5. It's a right-tail test, so the alternative, we see it's right-tail test, is that p is greater than 0.5. What this vertical line represents is the p-hat, the test statistic. To the right is our rejection region, and to the left is of that vertical line of the top represents when we don't reject. So if we reject improperly when the null hypothesis is true, that would cause the type 1 error. And that's going to always be based on whatever your significance level is, because you're choosing your significance level and determining based on that and the p-value. If the p-value is greater than the significance level, you're going to fail to reject. And if the p-value is less than your significance level, then you're going to reject. So the probability of making that type 1 error is based on whatever alpha you choose. The bottom normal curve, this one, is based on the alternative, and you actually have to choose a specific alternative to create this diagram. So in this case, they said, well, the true alternative, we'll call that PA, is 0.95. And so if you correctly reject your null hypothesis, remember to the right of this vertical line is when we're rejecting our rejection region. So if I'm correctly rejecting my null hypothesis, that represents the power of the test. If I fail to reject and my null hypothesis is false, well, that's my type 2 error. So we can see the complementary relationship between the power of the test and the type 2 error. For the AP exam, you're actually not responsible for calculating the power of the test based on a chosen value for the alternative, but you are responsible for knowing the relationship between the type 2 error and the power. What I mean by that is if I define beta to be 0.2, you should be able to calculate that the power of the test is equal to 0.8, 1 minus 0.2. For the AP exam, you're also responsible for knowing how you can increase the power of a test. And the following 4 factors are ways you can increase the power of the test. And that's by either increasing the alpha, the significance level, increasing the sample size, increasing the effect size, or decreasing the standard error. And we're going to go more into it on the next few slides. So let's go back to the example we started chapter 9 with. Recall that Mrs. Poland claims she's an 80% free throw shooter. Mr. Wilcox is skeptical and believes she's less than an 80% free throw shooter. Mrs. Poland has decided to take another SRS of 50 free throws to prove herself. So I'm restating my null and my alternative hypothesis. Notice that in this case, we're dealing with a left tail test. And suppose that my true actual free throw percentage is actually 66%. So we have an applet that can actually, and we're going to use that today, can actually calculate the probability of making a type 2 error based on the actual 66%, and it's going to be 0.24, and therefore the power of the test is 1 minus 0.24 or 0.76. So So the following diagrams shows what happens when we increase alpha. So to the left is the original one that I started the applet with, and that's when I have a significance level of 0.05. And to the right is when I increase my significance level to 10%. Let's understand the diagram first to the left. So my null hypothesis is 0.8, and the normal curve to the right represents the one developed from the null hypothesis, where p sub 0 is equal to 0.8. To the left is the one in the green and the blue. That represents the alternative hypothesis, so p sub a is 0.66. So that vertical line over here is that cutoff point. So in this case, to the left is my rejection region, so it's opposite from the first diagram we had, and to the right is when I fail to reject. So the region here, here's my cutoff, that's that 0.66. I'm sorry, that's my test statistic of 0.7, and this is the 0.66 from the second diagram. So the region from here that I'm highlighting in red, that represents the type 1 error. That's when I reject my null hypothesis improperly. Again, this is my rejection region. The green, that shaded green region, that represents when I'm rejecting my null hypothesis properly. In other words, that's the power of the test. And the blue represents my beta, my type 2 region, when I'm failing to reject my null hypothesis, when my null hypothesis is actually true. So now let's go to the right diagram. Again, the green is representing the power of the test. The blue is representing my type 2 error. So when I increase my alpha, notice that little region here is increased. So when I increase my alpha to 0.10, what happens is my beta is decreasing, my type 2 error is decreasing, and my power of my test, you can see this green region is much larger. My power has increased. And that's because when I increase my alpha, I have a larger area that I can reject. So there's a greater chance that my p-value is going to be less than my alpha of 10%. So I have a higher chance of rejecting my null hypothesis. My next slide looks at what happens when I increase my sample size from 50 to 125, and I notice that I'm keeping my alpha, my probability of making a type 1 error, both at 5%, so that's consistent. But otherwise, the diagrams are very similar to what we went over, okay? So the red represents the normal curve based on my null hypothesis of 0.8. My alternative, the one in the blue, and that shaded green and blue, that represents my normal hypothesis when my alternative is 0.66. Okay. And I'm comparing that to when I increase my sample size to now 125. And what happens is that when you increase your sample size, it decreases your variation. So that means there's less in the tails. So when there's less in the tails, notice that there's a greater notice how the power has increased. So if I keep my alpha the same and I increase my sample size, what ends up happening is I decrease my variation, and so there's less in the tails, and that actually decreases the ability of making a type 2 error, which therefore increases the power of the test. So what happens when you increase effect size? What the effect size is the number of standard deviations between the alternative hypothesis, what you believe the alternative hypothesis, and what the original hypothesis is. So how far apart those, how many standard deviations away those two are. So currently, from the diagram on the right, my null hypothesis I'm stating to be 0.8, and my alternative I'm stating to be 0.6. On the diagram on the right, here it's 0.8, and I'm saying my alternative is 0.5. So it's much further apart. Here it's 0.3 apart, here it's 0.14 apart. Okay, so notice the difference in the diagram. As I move the alternative, what I believe to be true, and the alternative farther and farther apart, notice what happens. So the effect size is increasing, and what's happening is my beta, my type 2 error, is decreasing. If you look at this blue region here, it's fairly large compared to here, it's almost non-existent, and therefore my power has increased. So let's go through an multiple choice question that you're going to have similar problems to. Medical researchers are testing a new surgical procedure to minimize the side effects of surgery. The null hypothesis is stating that the procedure is not effective in minimizing side effects. The null hypothesis, the procedure is not effective at minimizing the side effects, so the alternative is that the procedure is effective. For the researchers, the more consequential error would be that the procedure is actually effective in minimizing the side effects, but the test does not detect the effectiveness of the procedure. So when you're doing this problem, like I always restate the null and the alternative so it's more clear to me, and then you have to decide what this means, what the more consequential error means. So they're more concerned with the fact that they failed to reject, because if they didn't detect it, they failed to reject the null hypothesis when in fact they should have. So they're more concerned with making a type 2 error. So what you have to do is decide, well, what are ways that I can reduce having a type 2 error? Well, that you can reduce it and actually increase the power of the test. So they want to reduce the type 2 error. In essence, that means you want to increase your power of the test. So what are ways you can increase the power of the test? Well, you can increase the significance level. And so if you increase the significance level, that increases the probability of making a type 1 error. So that looks like a good choice, but let's go through the others. If you increase the significance level, it decreases the probability of making a type 1 error. Well, that's definitely not true. That's the opposite. If you decrease the significance level, that actually decreases the probability of making a type 1 error. If you decrease the significance level, that does decrease the type 1 error, but that would actually decrease the power, and that would